Hi everyone, today we're going to talk about buffer capacity. Tying to the learning objective from College Board, you may want to pause the video to read them. When we add acid or base to a buffer, it involves two kinds of calculations, one being stoichiometry. We write the neutralization reaction first, then we determine the moles of all species present, either added, reacted, and remaining. Then we have an equilibrium situation. We now use Henderson-Hasselbalch equation to calculate pH of the buffer. So remember these two steps, it will be immensely helpful to you. A solution containing 0.1 mole of acetic acid with 0.1 mole of sodium acetate has a pH of 4.74. Calculate the pH after 0.02 mole of sodium hydroxide, the strong base, is added. Step number 1, stoichiometry. Write the balanced net ion equation of the neutralization reaction, hydroxide added to the acetic acid to form acetate ion and water. Now we use the ice table. We set up with the moles of the substances given. We have 0.02 mole of the base, and we have 0.1 mole of the two components of the buffer system. Now the change is that the OH minus becomes the limiting reactant, so it is used up. And stoichiometrically, we take away 0.02 mole from the acetic acid and add 0.02 mole of the acetate ion to the product. Now at the end, we have 0.08 mole of the acetic acid and 0.120 mole of the acetate ion. Step number 2, now we use Henderson-Hasselbalch equation. pH is equal to negative log of Ka, 1.8 times 10 to the minus 5, plus log of the ratio, which is 0.12 over 0.08. And now we calculate the pH to be 4.92. Notice that the pH only increased slightly by 0.18 unit from 4.74 to 4.92, becoming a little bit more basic because the hydroxide ion is neutralized by the weak acid, acetic acid. Now the other part of the problem is now we are attacking this buffer with strong acid HCl 0.02 mole. So again, we use the balanced net ion equation, but this time we're adding the H plus to the acetate ion to form acetic acid and water. It is really important that you write the equation correctly so that you attach the right number for your calculation. The wrong equation will lead to a wrong calculation. So here we have 0.02 mole of the hydrochloric acid and 0.1 mole of both components of the buffer. And stoichiometrically, the hydrogen ion is the limiting reactant, which will be used up. We take away 0.02 mole of the acetate ion, and we add 0.02 mole of the acetic acid. So at the end, we have a ratio of 0.08 to 0.12, being the A minus to HA. Now we use Henderson-Hasselbalch equation. pH is negative log of Ka plus log of the ratio. And the new pH is calculated to be 4.57. So notice how the pH decreases from 4.74 to 4.57 because of the addition of the hydrochloric acid, but it's been neutralized by the conjugate base. Now, buffering capacity is the amount of acid or base a buffer can neutralize without a significant change in pH. If I have 1 liter solution containing 1 molar each of the HA and A minus to another buffer solution containing 0.1 molar of the HA and A minus, which has a greater buffering capacity. In other words, which can be more resistant to change in pH when I add strong acid or strong base to it. The answer is that the buffer with 1.0 molar component has a greater buffering capacity because it contains a larger concentration of HA and A minus to absorb the relative large amount of hydrogen ion or hydroxide ion present from the strong acid or strong base added, resulting in little pH change. So remember, the higher the concentration, the greater is the buffering capacity. Now, the optimal pH of a buffer is when pH is equal to pKa. If the weak acid HA and the conjugate base A- concentration differ by 10 times, then the buffering action is poor. Log of 10 is equal to 1. Therefore, the buffer acts effectively over a pH range of plus or minus 1. pH is equal to pKa plus or minus 1 for the buffer to react effectively. Given a problem, two buffer solutions, each containing nitrous acid and sodium nitrate. The following table shows the pH measurement before and after the 0.1 mole of HCl is added. Now notice that both buffers are pH 3.40 before I add the hydrochloric acid. But once the hydrochloric acid is added, buffer 1 dropped to pH of 3.23, while buffer 2 dropped to 1.3, quite a large change there. Explain why they both have the same pH initially, and then why the difference in the pH value after the HCl is added. Both buffers have the same pH of 3.4 because they contain equal molar, equal volume of HNO2 and NaNO2, the two components in the buffer. Now this is where you have the optimal buffer where the pH is equal to pKa. So here this shows the calculation of pH is equal to pKa or 3.40. In buffer 2, it contains the conjugate acid-base pair component at a higher concentration than in buffer 1. Therefore, buffer 2 has a greater buffering capacity to resist changes in pH. In buffer 1, the buffering capacity is actually destroyed because the components are too low in concentration relative to that of HCl. Therefore, now the excess HCl will decrease the pH of the buffer by a large extent. Now here is the calculation showing how it works. If we have 0.05 mole of the two components in the buffer, when we add 0.1 mole of hydrochloric acid, you can see that the nitrogen ions will be all used up. So leaving behind the hydrogen ion 0.05 mole and 0.1 mole of the nitrous acid. Therefore, the pH is determined by the remaining hydrogen ion, which is 1.3. That means the buffering capacity is now destroyed. Whereas with buffer 2, the situation is not the same. I have sufficient amount of nitrite ion and nitrous acid to combat or counteract the hydrogen ion. So in this case, the hydrogen ion is used up. And I have 0.4 mole of the nitrite ion and 0.6 mole of the HNO2 left. And using the Henderson-Hasselbalch equation, the pH is now calculated at 3.23, a slight decrease from 3.40. So it is still working effectively for the buffer. To sum up what we have learned today, we learned how to use stoichiometry and equilibrium concepts to calculate the pH of a buffer solution after small amounts of strong acid or strong base is added. We learned to explain why the buffer would resist changes in pH when small amounts of strong acid or base are added. We learned how to define the buffering capacity of a given buffer solution. And we also used quantitative calculations to reason how the different concentration of the components in a buffer could affect the buffering capacity. I hope that you find the video helpful. If you like it, please give us a like and please subscribe to our video. And hope to see you again real soon.